There we go. Okay.
All right. So everybody took the test yesterday and turned in their problem set. I haven't begun like the grading process, so I hope to work on that this weekend. We're gonna keep working through this chapter on the applications. We had one or two problems, I think. Yeah, I guess 3 problems to finish on the curvilinear motion, and then we'll look at related rates problems. And then depending on where we're at on time, we might get a start on the curve sketching. We'll just sort of see where we're at the end of the related rates. So one important announcement is we're going to have a quiz on Tuesday. So not next Friday, but Tuesday, because if I wait till next Friday, then the quiz is just going to cover so much material. So I thought it makes more sense to do that on Tuesday. And it'll just cover some application problems. Again, not more than 4 problems, but maybe a curvilinear motion or related rates. See how far we get in this curve sketching business by the end of tomorrow. Before we jump in to our notes, does anybody have any questions on exercises or some of the examples we worked out the last time we were in this section?
That's fine. Sorry, they need more volume.
Oh, okay.
There we go.
Okay, is that better?
Yeah.
All right, so hearing no questions, I guess we'll just kind of jump in. Recall that what we did last time, and by the way, I seem to have lost like the set of notes that I had already completed. Like I have the PDF and it's posted, so I can't just scroll back and refer to the ones that we did before. But in this curvilinear motion, right, velocity is a vector. And the way we approach these is we need to find the components, right? We need to find the x and y components. That's what we need to use calculus for, because Vx is dx dt and Vy is dy dt. And once we have those components, we can use Pythagoras and the arctan function to get the magnitude and direction. So in the last one that we actually finished, and again, I don't have the finished version here, but they gave us the pair of parametric equations, right? One equation for x and one equation for y. Those are both functions of t. So finding dx dt and dy dt is pretty straightforward. In this next example, they tell us the path that it moves along by giving us kind of the usual kind of equation we expect, which is, we call it a rectangular equation. Y is a function of x. Now we still need to find dx dt and dy dt. So what they do here for us is they've told us the path in the rectangular equation, and then they say the horizontal velocity Vx is constant at 6 centimeters per second. So first of all, they've told us that dx dt is 6. As a function, it's always equal to 6. And that's important information. They gave us the x component at 6, so really our work, what we're going to work hardest on at first, is finding that y component. Because once I have the y component, then I've got both of them, and I can use Pythagoras and arctan. So the equation we have to work with is this one right here. And if I want the y component, I have to differentiate with respect to time. So if we differentiate with respect to time, we have dy dt equals, on the other side, this is an implicit differentiation problem, right? So we're going to use our power rule as usual, 2/3, 2/3 x, but I'm respecting t, and this is an x, so I have to multiply by dx dt. So this is the chain rule. Right, for implicit differentiation. And we know what it's equal to, right? It's constant at 6. So 2/3 times 6 is 4, so we get, as a function of x, dy dt is 4x. And having dy dt as a function of x is actually helpful because we want the velocity at the point. They give us the coordinates that we're interested in. So vx is going to be equal to, or sorry, vy is going to be equal to dy dt when x is equal to 2. So we get Vy equals 8. Now, they already gave us Vx at 6. So Vy is 8, Vx is 6. What quadrant is this vector in? The first quadrant, yeah. So that means that when I find the angle, I don't have to make any adjustments for the quadrant. Like I'm going to use arctan, and whatever arctan spits out is the angle that we need. So there's the first part. This is the part that required calculus. So now we're going to find magnitude and direction. To get magnitude, we use Pythagoras. And the square root of 6 squared plus 8 squared is 10. The magnitude is the part of the answer that has the units. So this will be centimeters per second. It inherits the units that they used when they told us what Vx was. And theta is arctan of Vy over Vx. It's always the y over the x. And you know, before, and usually what we do is we say we have to make sure everything's positive, and we put like the absolute value signs. This is a first quadrant vector, so I know that just plugging in the Vy over Vx is going to give me what I need. .1 degrees. And so I'm just going to kind of put it together to give a single answer. This velocity vector is 10 centimeters per second at an angle of 53.1 degrees. Questions on that example? Okay. All right, so moving on, our next, in curvilinear motion, right, we've been finding velocity vectors. We can also find acceleration vectors. A vector is anything with magnitude and direction. So acceleration has magnitude and direction. It is the rate of change of velocity. And so that means that if we have, say, x and y functions, when we find the components for the acceleration, we're going to be looking at the second derivative with respect to time to get those components. So in example 3.6, they give us a pair of parametric equations. And we want the acceleration when t is equal to 2. They didn't give us any units here, so our answer will be unitless. But getting started is just like getting started with the velocity problem. I need these components. And I'm going to find these components by differentiating with respect to t. So if x is t cubed, dx dt is 3t squared. And because this is acceleration, I want the second derivative with respect to t, which gives us 6t. And we want the acceleration when t is 2, so that x component for acceleration is 6 times 2, or 12. And we're going to do the same thing for the y function. So y is 1 minus t squared. dy dt is negative 2t, and the second derivative is negative 2. So the second derivative is constant, which means ay is negative 2 at all values of t, but certainly when t is equal to 2. What quadrant is this vector in?
Four.
Yeah. Positive x, negative y, that puts it in quadrant 4. We've used calculus to get what we need, and now we're finding magnitude and direction, so Pythagoras and arctan. So let's get that magnitude. That is the square root of 12 squared plus negative 2 squared. 144 plus 4 is 148. So that square root is 12.17. Now, if they had included units in this problem, units of acceleration are like centimeters per second squared or feet per second squared. It's your displacement over time squared. But we didn't have any units in this problem. And then the angle, it's in quadrant 4. So a quadrant 4 vector, when I find arctan of like the positive ay over ax, that's going to give me the measure of this angle. And so to find the standard position angle here, I'm going to take 360 and subtract alpha. So 360 minus arctan of, and I'm just going to plug in the positive components. So Vy or Ay over Ax, making the positive is 2 over 12. .5 degrees. And that's the standard position angle. Some folks will say, might give that like the acute reference angle and just say it's that would be 10 point something degrees below the positive x-axis, and that's okay to state it that way. If you do that, just make sure you give the reference that from which you're measuring. But our acceleration vector is 12.17 at an angle of 350.5 degrees. Questions on this example before we do one more?
Here, arctan, why did you not use a negative 2?
Because what this gives us here is the reference angle alpha, or theta ref, I think is what I called it in the notes before. But I'll just say the reference angle, which is always an acute angle. So what we've done is we've said, okay, if I want this angle theta, what I'm going to do first is find the measure of alpha as an acute angle in the first quadrant, and then just subtract that, go backwards from the 360 to get that fourth quadrant angle. So we always find that reference angle by finding arctan of positive absolute Vy over absolute Vx. We didn't have to do that in the last one because it was a first quadrant angle. So, I mean, I wrote it out this way, but I could have put the absolute value signs there. It's just that our components were already positive. And it's a first quadrant angle, so I didn't have to make any adjustments. Arctan will never give you a fourth quadrant angle, or when it does, it'll give it to you in the form of a negative angle. And what we want is a standard position angle measured counterclockwise from the positive x-axis. Other questions? Okay, let's try one more. A package of relief supplies dropped and moves according to these parametric equations. So again, they've given us a set of parametric equations, one for x and one for y. This time we do have units. The position is in meters, time is in seconds. When we find acceleration, it'll be in meters per second squared. We want to find both velocity and acceleration. So we can start out by getting these components, right? We know the velocity components are given by the first derivative with respect to time, and acceleration is given by the second derivative. So we could start maybe by working with our x function. X is 45t. Let's find our derivatives. dx dt is just 45, and the second derivative of constant, is of course 0. So what we found, that the first derivative is constant, so that x component, we want to find the velocity and acceleration when t is equal to 3. Well, dx dt is always 45, it's constant, so vx is equal to 45. And again, the second derivative, also constant, so certainly when t is 3, it's going to be equal to 0. Whoops, that's not Vy. That is Ax. All right, we're working with the x function. So we now know the x component for both velocity and acceleration. Let's do the same thing with the y function. So y is negative 4.9 t squared. dy dt, just using the power rule here, 2 times 4.9 is 9.8, so we get a negative 9.8 t. And that means that if we want the y component, we're going to plug in t equals 3. Which gives us negative 29.4. To get the y component for acceleration, we'll differentiate again with respect to time. Differentiating the function negative 9.8t just gives us the constant negative 9.8. And so ay is negative 9.8. That kind of makes sense. I mean, I don't know if how much physics you've done, but when we see that ay is negative 9.8, what that means is that acceleration due to gravity is 9.8 meters per second squared in the downward direction, which might be a familiar figure if you've done any physics. So we have all the components we need. Calculus has done its job. Now we're going to use Pythagoras and arctan to find our vectors, the magnitude and direction. So let's do velocity first. Our Vx is 45. Our Vy is negative 29.4. Throwing that in the calculator gives us... Be really careful when you're, if you have negative components, the calculator is a stickler for the order of operations. So if I'm plugging in negative 29.4, I've got to put it in parentheses and then square it. Otherwise, it will subtract it inside the radical. We get 53.75. What are the units on this?
Meters squared.
Not meters squared, so it's velocity, right? Think about the units that we expect for velocity. It's a rate of change of displacement.
Meters per second squared.
Meters per second. Just plain old meters per second. Now we're going to find the angle, the direction. What quadrant is this vector in?
Four.
Yeah, positive x, negative y, that puts it in quadrant 4, like the last one. So that means that we're going to find, like, this reference angle here by plugging in only positives to the arctan and then subtracting from 360. So positive 29.4 over 45. Subtracting that from 360 gives us 326.8 degrees. So that means that our velocity vector, putting these together, 53.75 meters per second at 326.8 degrees. For the acceleration, right, let's set this up, like the way we've been doing this, right? We know we're going to use Pythagoras to get the magnitude. We want to use arctan to get that direction. The components, the x component is 0. The y component is negative 9.8. Now, we could set up Pythagoras, but I don't think we'll need a calculator to do this. What should we get? Say that again? Yeah, 9.8. It's positive, magnitude's always positive, but that should make sense, right? This vector, if the x component is 0 and the y component is negative 9.8, this vector is just straight down, right, at 9.8. So its magnitude should be whatever that y coordinate is, whatever that y component is. Now, let's think about the angle. If we try to find arctan of 9.8 over 0, I think we encounter a problem, right? We're definitely going to get an error. We can't divide by 0. So this isn't really going to serve us well. But look at where this vector is, right? So I drew that vector, it's straight down. What angle is that?
$270.
Yeah. So, when I'm working with vectors, we have this kind of analytic way of approaching it. We're finding derivatives, and then we have magnitude and direction, Pythagoras and arctan. But I find it's always helpful when I know what the components are, is it doesn't have to be super accurate, but I do like a really rough sketch. Where is this vector located? Like when we were doing the velocity vector up here, I just sketched this vector. I said, oh, I know it's in the 4th quadrant. That helps me remember that I have to subtract from 360. And sketching this vector, seeing that it's 9.8 magnitude of 9.8 straight down helps me realize, okay, it doesn't bother me that I can't find arctan of this, because it's not in the domain of that function. I can't divide by 0, but I can still find that angle, and it's easier to see when I visualize it. So the acceleration vector is 9.8. Now these units are meters per second squared at 270 degrees. Questions on that example? Okay. All right. So our next section is on related rates. These are all word problems. I mean, I guess curvilinear motion is also word problems. These different word problems that we encounter in calculus. There's curvilinear motion. Right now we're doing related rates. Later on we're going to do these optimization problems. So we have these different types of word problems. And one of the things we want to be able to do is when we read a word problem, be able to pinpoint, oh, this is a curvilinear motion problem, or oh, this is a related rates problem. They all kind of read in a similar way, like the problems in each category. Curvilinear motion problems, I think, are pretty easy to recognize just because they'll say find the velocity, find the acceleration. These related rates problems always go a certain way. Like they'll describe a scenario that's where things are changing over time, right? And they'll tell you how fast one quantity is changing, and then ask you to find how fast another quantity is changing. Related rates. How does the rate of one thing affect the rate of some other thing? So when I'm reading these problems, I read it carefully. I try to figure out what they're telling me. Identify whatever quantities they're working with. Sometimes a sketch is helpful, not always. And then I want to figure out how those quantities are related to each other. This part has no calculus, right? We'll see, for example, in this first example in the notes here, they talk about a spherical balloon being blown up, and then they refer to its volume, and they talk about the radius. So when that step 3 in this problem is going to be like, oh, I need to go find the volume of a radius formula, and that'll give me the formula that relates only V and R together. And then what I want to do is differentiate with respect to time. These are all time rates of change in related rates. They tell us how fast one thing is changing, and then we want to figure out how fast another thing is changing. And then we should be able to solve that problem. In this first example, again, I've already said, we've identified the quantities, right? We know that we're interested in the volume of a sphere as a function of r, of its radius. And if you look that up in, any number of places, you can search it online, or probably it's in the inside cover of one of the textbooks or something, but you find that v is equal to 4/3 pi r cubed. You won't, I don't expect everybody will have that memorized. If there was some of these geometry formulas that come up, if there's a problem like this on a quiz or a test, I just include it in the problem. Like, remember that the volume of a sphere is given by this formula. So there's our equation. There's no derivatives in that equation. Before I think about differentiating, I just want to figure out what did they tell me? What do I want to find out? They say that the volume increases at the constant rate of 2 cubic feet per minute. That's a rate. And if there's one thing that we get out of this semester, and I hope that we get more than one thing out of this semester, but if there's one thing that we get out of a first semester calculus course, it's that a rate is a derivative. A derivative is a rate of change. So when they tell us the rate at which something's changing, they're telling us its derivative. So we know, what we know here is that dv dt is equal to 2. It's constant at 2. And now they're asking us to find another rate, find the rate at which the radius is increasing when it is 3 feet, when the radius is 3 feet. So that's what we want. The rate at which a radius is increasing, that's dr dt. And we want to know what it is when r is equal to 3. Before we go any further, are there questions on how we've parsed out this problem and identified those rates that we were given and what we want? Okay. So I know dv/dt, I want dr/dt, so my next step is I would like to have an equation that with dv/dt and dr/dt. So I'm going to take this equation, v equals 4/3 pi r cubed, and I'm going to differentiate with respect to time. On the left side, if we differentiate with respect to time, we just get dv/dt. On the right side, using the power rule, let's see, we get 4/3 pi times 3r squared. Now, I'm doing this with respect to time. So what do I need right here? Mm-hmm. dr dt, because we're taking the derivative of an r term with respect to t. So we have to add that factor. That's the chain rule at work. That chain rule is pretty much always going to be a part, like the chain rule like we see it play out here is pretty much always going to be a part of these problems. If I forgot that, I'd be in trouble, but hopefully be able to recognize it, because if I forgot that chain rule, I'd have an equation that doesn't have dr dt in it, and I'd be hard-pressed to find the value of dr dt if I don't have an equation with dr dt. So that might prompt me to go back and try to find an error. All right, so what we know is that dv/dt is always equal to 2. dv/dt is always equal to 2. So I can plug that in now. We want to find the rate at which the radius is increasing when r is 3. So what I'm going to do right now is I'm going to hold off on plugging in r equals 3 just yet. You could at this point if you want to, but I'm going to just do some algebra and solve this, find dr dt as a function of r, and then plug in r equals 3. What's really important to understand, though, is even though we're interested in figuring out what's happening when r is equal to 3, we absolutely cannot plug it in at the get-go. We're not setting r equal to 3 in the original equation because r is changing over time. This balloon's being inflated. You have to wait until after you take the derivative to plug in the values of any quantities that are changing. So let's see, cleaning this up a little bit, those 3's cancel. So we have 4 pi r squared dr dt. We can divide by 4 pi r squared. And we find that dr dt is, let's see, after reducing 1 over 2 pi r squared. So I have dr dt as a function of r. I'm ready to just plug in r equals 3. Nine to 18 pi in the bottom. That would be dr dt. What should the units of dr dt be?
B.
So that's units of r. What about the rate of change? Oh, sorry, say that again.
Per minute.
Feet per minute, yeah. So the units of r were feet, the units of t were minutes. That gives us feet per minute. There it is as an exact value. In applied problems, we often approximate. So in the calculator, 1 divided by parentheses 18 pi, 0.0177 feet per minute. Questions? Okay, let's try another one. Let's just read through this. They say that the kinetic energy in joules of an object is given by K equals 1/2 mv squared, where m is the mass in kilograms, v is its velocity. They say we've got a 250 kilogram wrecking ball, accelerates at 5 meters per second squared. How fast is the kinetic energy changing when v is equal to 30 meters per second? So, look, I don't have to have a background in physics. Like, I don't have a background in physics. I'm just going to tell you that right now. But I do know how to kind of parse out these word problems that we get. And that's a skill in and of itself. So I know in this problem, they're giving me one rate, and they want me to find another one. So I got to identify those. They gave me an equation, K equals 1/2 mv squared. So I'm just going to jot that down.
Yay.
So somewhere they gave us the rate of one of these quantities. I don't know which one it is yet. And then they're asking us to find another rate. So they tell us that it accelerates at 5 meters per second squared. And then they say, how fast is the kinetic energy changing when v is equal to 30? So that's what they're asking me to find. If we want to know how fast kinetic energy is changing, what we want is dk dt. When v is equal to 30. So that, I'm going to stop right there and just say, look, we want dk dt when v is equal to 30. What that means is we're hoping that the original equation, before we take any derivatives, we want to be able to get an equation with only k and v. Only k and v. The equation we have has k and v and m, the mass, but they told us the mass. Now, as this wrecking ball is swinging, doing its thing, the mass doesn't change, right? The mass is constant. So I know that I could just plug in m equals 250. Because the mass is constant, is not changing at all, I can plug that in right away before I take derivatives. So I'm going to do that. So there's my equation that relates k and v. I know that the rate I want is the rate of change of k. So hopefully what they've done is given me the rate of change of v somewhere. So this is hopeful thinking here, where I'm just writing down dv dt. At some point, do they give us dv dt? Is there a piece of information that can be interpreted as that derivative?
The wrecking ball acceleration.
Yeah, acceleration is a rate of change of velocity. So, we kind of think about acceleration just being a second derivative of position, which it is, but it's also the first derivative of velocity. So they tell us that it accelerates at 5 meters per second squared, so we know that dv dt is 5. So now I think we have everything set up so that we're ready to take the derivative on both sides with respect to t. So dk dt, what do we get on the right side? Can you say that louder?
250.
dv dt, I think I heard, I hope. It's a little bit quiet, so I have trouble picking up everything that you're saying. Yeah, so we just remember that we need that chain rule. It would be kind of obvious if we didn't have the chain rule, like, you know, we'd notice that there's nowhere to plug in dVdt if I forgot to apply the chain rule. So we know that that dVdt is 5. We'll go ahead and plug that in now. Uh, 5 times 250, 1250. So now I have dk dt as a function of velocity, which is perfect for us because we want to find dk dt at v equals 30. So $37,500. And the only question that remains is what units should we have on this value? We want to kind of scan the problem, keep in mind that it's dk dt, so let's use that form to help guide us figure out what our units should be.
Joules per second?
Joules per second. Yeah, kinetic energy is measured in joules, and our time is measured in seconds here. Questions on that example? Okay, before we go on to the next one, I'm just going to emphasize again, try to be really aware of what quantities are changing and what quantities are fixed. In this problem, the mass was fixed. The mass of that wrecking ball wasn't changing. That's what allowed us to plug in m equals 250 from the get-go. But the velocity does change over time, and that's why we had to wait until after taking the derivative before we could plug in v equals 30. We have got one more. This problem is probably in, as an example, in just about every calculus textbook published. A ladder slipping down along a vertical wall. And so if you could imagine, if I kind of let's say here's our vertical wall, here's the ground. I've got a ladder that's slipping down. So as the top slips down, the bottom has to kind of kick out away from the building. They tell us that the ladder is 10 feet long, and that's a fixed quantity. The top is slipping at a constant rate of 10 feet per second. And we want to know how fast is the bottom of the ladder moving along the ground when the bottom is 6 feet from the wall. So we want to find however many feet per second it's moving outward. So this is a problem where I think it is crucial to kind of draw that little sketch because they don't refer to like a geometric figure, you know, like we had the sphere problem. We're like, oh, volume of a sphere, I can go look up that formula. And the last one, they gave us that kinetic energy formula. Here, they don't refer to any formula that we're going to use, but describing what happens when we visualize it. I'm going to assume that this building was erected so that it's perpendicular to the ground, as most buildings are. I think that's a reasonable assumption. And now I got to throw some variables in here. So we're talking about the rate at which the top is slipping down. That means that vertical side from the ground up to the top of the ladder is changing. And now the horizontal side from the corner of the building out to the end of the ladder, that's changing. I'll call this quantity along the bottom x, and this quantity from the ground to the top of the ladder y. And once we have this sketch, it's pretty clear that we can make an equation that relates these quantities, x and y, those distances, just using Pythagoras. So we know that x squared plus y squared equals 10 squared. Now they gave us some rates, or they gave us one rate and asked us for another, as is the case in all these related rates problems. So the rate we know. They tell us that it's the top of the ladder is slipping down at 10 feet per second. So that tells us how y is changing, right? As it slips down, y is decreasing at the rate of 10 feet per second. So that means that dy dt is negative 10. Negative because it's decreasing. Y is getting smaller. dx dt is the rate we're looking for. How fast is the bottom of the ladder moving out from the wall? That's the rate of change at which that distance from the corner to the end of the ladder is moving. So, or changing. So we want dx dt when the bottom is 6 feet from the wall, that's when x is 6. So we know dy dt, we want dx dt. We have an equation with just x and y as our only variables, which means we're in pretty good shape. The next thing we can do is take the derivative. Let's differentiate with respect to time. What equation do we get when we differentiate this with respect to time?
Two x plus 2y dy equals 0.
So 2x what?
2x plus 2y dt.
Like this?
Yeah.
Equals 0. You're really close. We're missing one thing.
2x, yeah.
Yeah. We're respecting time, so whenever we take the derivative of a term that's not a t term, we have to use the chain rule. We would probably have figured out before we got too far into this problem that we forgot something, because keep in mind over here, and this is one of the reasons why I start out by trying to write out what we know and what we want. We want dx dt when x is equal to 6. So if I forgot that dx dt, I would find it pretty hard to solve for dx dt if I don't have it in my equation. They tell us that dy dt is negative 10, so we can plug that in. So 2x dx dt, that would be minus 20y is equal to 0. We could solve this for dx dt. Throw the 20y on the other side, divide both sides by 2x. And after reducing, we have 10y over x. Now, a lot of the time, in fact, well, in the couple examples that we already did, by the time we solve for the derivative, you know, like that we're after, we're at a point where we could just plug in the value and get our answer. But now look at where we are here. We want dx dt when x is equal to 6. So we know what to plug in for x, but our expression also has y. So what we need to do before we can actually finish solving this is find y when x is equal to 6. So we have something to plug in for both of those coordinates. And to do that, I'm just going to use the original equation. So 6 squared plus y squared equals 10 squared. 10 squared minus 6 squared is 100 minus 36 is 64. And that means that y is equal to 8. I know that, you know, given the restraints of the problem, y is going to be a positive, so I don't need to consider the negative root there. And now it's all over but the shouting. Plugging in 8 for y and 6 for x gives us, let's see, I could cancel a 2 out, so 40 thirds. There it is as an exact value. What would the units be?
Feet per second.
Mm-hmm. Because x is measured in feet and our time is measured in seconds. And then we could approximate 40 thirds, about 13.3 feet per second. We got a positive value for dxdt, which I think should make sense, right? If this ladder at the top is slipping down the wall, the bottom is kicking out, that means that x should be increasing. I made sure that when I wrote down the derivative that I knew, that dy dt, I took into account that that meant that that distance y was decreasing, which gave me a negative derivative. And when I did that, that means that I should get a positive derivative when I find dx dt. Questions on that example? Okay. All right. Let's see. So we have about 20 minutes left. Why don't we go ahead and get a start just kind of talking about some of these principles that we're going to use in the curve sketching. We won't get very far, but we'll kind of lay a bit of a foundation. And the first thing I want to say about curve sketching is that a lot of people wonder when they're learning curve sketching, like, why do I learn curve sketching? You know, like if I want to sketch a curve, like we have calculators that could do it. We have calculators that could sketch curves that are more accurately than we can do it by hand. The reason that it's still a part of a calculus course is because what we do when we do curve sketching is we gather all of our knowledge about analyzing how a function changes, all of our knowledge about what derivatives, first and second derivatives, can tell us about the behavior of a function, and we analyze it. The curve sketch is really just a proxy for us being able to understand how to take a function, analyze its behavior, and then give a result and describe how that function behaves. So it's the goal, you know, the curves, sketching an actual curve is a goal, but we should think of it as a stand-in for everything that I'm able to do to understand how this function behaves. And we're going to start by going back to the first time that we really were developing this idea of what a derivative is, was when we were talking about the slope of a tangent line. So here's just a curve, some y equals f of x. If I were to kind of pinpoint, take a look at what's happening here, right, that slope is positive. That slope is positive, and that means that the first derivative is positive, right? F prime of x is greater than 0. If I pick some point in the middle here, where this curve is decreasing, we have a negative slope, or f prime of x is less than 0. And then over here again, on this other side where it's increasing, we have a positive slope. We have already done some of this type of analysis before when we were working with slopes of tangent lines and then looking at a graph, but we're just kind of summing it up, just saying, look, I can tell. If I want to know where a function is increasing or decreasing, all I need to do is look at the derivative, find the derivative, and figure out where the derivative is positive and negative. And that'll tell me where the function itself is increasing or decreasing. And what our goal is going to be is to find the intervals, like find everywhere, not just find the derivative at a point and then say, oh, is it increasing or decreasing? But start with a function, use the derivative to find the intervals on which a function is increasing and the intervals on which it's decreasing. Let's do an example. We're going to do one of my favorite things, which I know you think I'm going to say completing the square, but that's not what we're going to say. We're going to use a sign chart. We're going to be able to determine where a function is increasing or decreasing without almost ever needing to plug in any value anywhere. So they give us a function here. F of x is x cubed minus 3x squared. And in this section, we are going to restrict ourselves to just polynomials for this section. In the next section, we're going to do more curve sketching, and we'll expand our family of functions to include other types of functions like rational functions. So we just want to know, where is this polynomial increasing and where is it decreasing? That means I'm going to find where f prime of x is positive and where it's negative. So, okay, my function f of x is x cubed minus 3x squared. I'm going to find f prime. A nice simple power rule derivative, 3x squared minus 6x. Once we have the derivative, our next step is to factor it. We want to figure out, in order to figure out where this is increasing or decreasing, I want to be able to look at its factors. And we'll see why in a second, why that makes it so much easier. So I'm going to factor out, a 3x. And so we get 3x times x minus 2. There's our derivative. This is a useful form for the derivative for our purposes. We want to know where it's positive and where it's negative. First, we're going to find out where it's 0. So at what values of x is the derivative equal to 0?
2.
At 2, yep. And what else? 0, yeah, because we have a factor of x. Okay, now we have everything we need to make a sign chart. We're making a sign chart for the derivative, for f prime of x. So here's how it looks. The bottom, the horizontal axis on the bottom, that's like a real number line. The vertical axis, I'm just going to list out the factors and then the derivative. So I'm going to have a row for the factor 3x. I'm going to have a row for the factor x minus 2. And then I'll have a row at the bottom for the product 3x times x minus 2. The horizontal axis, as I said, that's the real number line. I'm going to put these two values that we found where the derivative is 0, I'm going to mark those down. Those are the only values we need. We just have to make sure we put them in order because it is a proper number line. And now I'm going to fill in each row. And all I'm going to do is figure out where it's positive and where it's negative and where it's 0. That's all I'm going to mark down. Okay? So 3x, that is 0 when x is 0. If I plug in something less than 0, if I plug in something negative, 3x is negative. And if I plug in something bigger than 0, 3x is positive. Similarly, in the next row, x minus 2, that is 0 when x is 2. If I plug in something less than 2 to x minus 2, like let's say I plug in 0, I get a negative. I'll get a negative for any value I plug in that's less than 2. And if I plug in a value that's greater than 2, something greater than 2, and I subtract 2, the result is still going to be positive. So we didn't have to do much arithmetic here. Like, we didn't have to plug much stuff in. We just kind of figured out where it was 0. We had these nice linear factors. You know, there's not an x squared factor. It was just these nice x to the first power. Like, these 3x is linear, x minus 2 is linear, and the nice thing about a linear factor is that it's 0 exactly once, and then on one side of the 0 it's all negative, and on the other side of the 0 it's all positive. Now we're going to just put these two rows together to fill out the last row. So the derivative itself is 0 at these two values. For values less than 0, so we've split up this number line, right? I can see it as 3 intervals: less than 0, between 0 and 2, and greater than 2. At less than 0, 3x times x minus 2 has me multiplying two negatives together. What does that give me? Positive. In between 0 and 2, I would be multiplying a positive times a negative. What does that give me? Gives me a negative. And then at values greater than 2, I'm multiplying two positives together. And so again, that's going to give me a positive. And from this sign chart, we can answer the question. F of x is increasing when, let's see, when the derivative is positive. So that's when x is less than 0, or when x is greater than 2. So those two intervals. And f of x is decreasing when its derivative is negative, so that's from 0 to 2. So I've written these intervals in like inequality notation. You could also use interval notation. That would look like, for the first one, negative infinity to 0 union with 2 to infinity. And this would be 0 to 2. They're all open intervals. We don't include the endpoints because at the endpoints the derivative is actually equal to 0, so it's neither increasing nor decreasing there. Questions on that example? So when we started this problem, right, when we took the derivative, we were getting ready to make the sign chart. The first thing we had to do is find out when the derivative is 0. You know, we're interested in when it's positive or negative, but in order to do that, we had to find where the derivative is 0. And we know it's neither increasing nor decreasing there. So I guess that begs the question, like, what is happening at those values? Finding where the derivative is equal to 0 is of such great interest to us. We give it a special name. We call those critical values of a function. And a critical value is defined to be values where the derivative is either 0 or not defined. You know, so if maybe if I find the derivative, I plug in that value, it gives me 0, it's a critical value. Or if it makes me do something like divide by 0, you know, so it's not defined, that's also a critical value. What's useful to know about critical values is that if I'm looking for a maximum or minimum, those extreme values can only occur at a critical value. It doesn't mean that every critical value corresponds to an extreme value, to like a maximum or a minimum, but it means that if I have a maximum or a minimum, it will occur at one of those values. So it gives me candidates, right, to check. So real quick, I'm just going to kind of lay out this idea. And we can use like sign charts that we made, like the one we made in the last example, to figure out where it's increasing or decreasing. We can also use that sign chart to figure out where we have maxima or minima. So here I've just drawn, you know, like a generic maximum on the left and a generic minimum on the right. So imagine that, you know, I'm going to just draw in some axes here. So this is a maximum. Let's say this occurs at this critical value C. At this critical value, we know that the derivative f prime of C is equal to 0. To the left, f prime of x is greater than 0. It's positive. To the right, it's negative. So this point at C, f of C, at the top there, is a maximum when the derivative goes from positive to 0 to negative. It's increasing, it levels off, it's decreasing. That's what gives us a maximum. Over here on the other side, at this critical value that gives us a minimum, here we know that f prime of C is 0. And then on the left, f prime of x is less than 0, it's decreasing. On the right, the derivative is positive, because it's increasing. So the point C, f of C, is going to be a minimum when the derivative goes from negative to 0 to positive, right? It decreases, it levels off, it starts increasing. So if we kind of return to, in this next example, we're actually returning to the last one. In this example, I've just recreated the sign chart that we already made. That's what the sign chart looked like. So we knew when it was increasing and decreasing. At these places where the derivative is 0, we look at what's going on either side. Does x equals 0 give us a maximum or a minimum? Maximum? It's right, it's increasing, it levels off, it's decreasing. Then the other side here, at x equals 2, what does that give? A minimum. Yeah, because it's decreasing, it levels off, and then it's increasing. Now, when they ask us to find, it says find any relative maxima or minima. A couple things. When we're asked to find a maximum or minimum, they mean the whole point. We know that the maximum occurs when x is 0, but the maximum value is the y-coordinate. Right? So when we're finding maxima or minima, we got to find those y-coordinates. So let's do that. F of 0 is equal to 0, so that means the max is 0, 0. And f of 2, if you plug that in, you'll get negative 4. And that means that the point 2, negative 4 is a minimum. Also, they are relative maxima or minima. They're not like absolute maximum or minimum values. That's not what the first derivative is going to detect for us. In fact, if we use this information, we could get a rough sketch here of what's going on. Right now we have 2 points, right? We have 0, 0 and 2, negative 4. So there's 0, 0. Let's say this is 2. Negative 4. We know that we have a max at 0, 0. We have a minimum at 2, -4. We know it's increasing heading into the max. It changes direction. It's decreasing heading into the min. And then it's increasing forever thereafter. I know it doesn't change direction again because if it did, I'd detect another critical value. Right? Those critical values tells us where the function kind of turns around. Heading out of the max in the left direction as x gets more and more negative, it doesn't turn around again. If it did, I'd find another critical value. So it has to look something like this. We're going to learn more and in fact see what the second derivative can tell us about the behavior of a function as well. But this is probably a good stopping point. I know we're almost out of time. If you have questions, before we have class again tomorrow, if you have any questions before then, just send an email or a text. Otherwise, we'll kind of pick up where we left off. The beginning of class, as always, will be for your questions. So as you start on the practice exercises, maybe think about if there's any problems that are particularly challenging. Bring them up at the beginning of class tomorrow, and we'll cover those before we do more curve sketching. Enjoy the rest of your day.
You.